Okay, 2 o'clock. So let's start. What is it that we're doing? Cyclic groups, okay? The simplest kind of groups. Because you have one element that gives you everything. Very simple. Okay. How do we define them? Well, a cyclic group is a group where if you have one element and you just take its powers, negative powers and zeroth power, you get everything. So like this. And what we do, well, what we didn't do is the proof of this theorem 4.10. So that's the thing that we're going to do now. Okay. Theorem 4.10 says that if you have a cyclic group, then any of its subgroup is cyclic as well. Okay. So what we need to prove is that we have a cyclic group and we have a subgroup of G. Okay, and we want to prove that this H is also cyclic. That's the whole idea. That's what the theorem is telling us. So there is one case which is kind of elementary. So case 1, and H is just the identity. Now we're going to deal with it separately, but then H is generated by this identity, so it's cyclic. Okay, that was simple. Half of the proof done, basically. There's only a case 2 now. Case 2. H is anything else, then H is not. Just the identity. But then H contains, so what is G? G is generated by A. H is a subgroup. So H is something like, it's not just the identity, so it contains another element than just the identity. And the element that it contains has to be A to the K, because everything in G is A to the K for some K. For K Z and K non-zero, that's the other element than the identity. So at least this one has to be there. But also it contains A to the minus K because it's a group. Yeah, so if it contains A to the K, it has to contain in its inverse as well, and its inverse is A to the minus K. So it has to contain that. So if K was negative, then minus K is positive. And if K was positive, then minus K is negative. But in any case, it does contain A to the K for some positive K. Okay, so it does. So H, no, I shouldn't be saying it because it's too vague. So H contains A to the K for some positive K. Positive integer K. Okay, so so far so good. Now what I want is, what do I actually want? I want this H to be generated by something, by one element. And the one element that I want it to be generated by is going to be something in the form of A to the K. And what is the best candidate among them? Well, I take the least positive K. Because then, you know, so it's like, if I have A to the 3 and A to the 6, then A to the 3 generates A to the 6, but not the other way around. Okay, so so what I want is m to be the least positive. So I want m to be the minimum k such that a to the k is in H and k is bigger than 0. So among all those a to the k's that are in the subgroup, I pick the one with the smallest m, with the smallest exponent. And that's the exponent is m. Now I claim that the subgroup is actually generated by this least power of m, least positive power of m that appears in m. Now, how do I prove this? Well, if I'm by the standard typical way of, in these cases, very often, when you have two sets and you're claiming that they're equal, you want to show that one is a subset of the other and the other is a subset of the one. Well, so you show that anything in H is in that set as well, and anything in that set is in H as well. Right? Now, if you have both ways, then the sets have to be equal. Is everybody asleep now? Never mind. I'm not allowed to fall asleep, so I will just continue. So how do I prove this? Well, obviously, this is a subset of H. Why is that? Well, a to the m is in H, and H is a group, so all the powers of something that is already in the group also have to be in the group because it's closed. Okay, so anything that is of the form a to the m to the something is in H as well. Closed under the operation.
Yeah. Yeah. And the powers of the operation. Wait,
Yes,
what?
that's one of the powers.
I've been writing this like sentences by accident because I've been writing down what the actual words are saying instead of what his maths is saying.
It's a very good idea.
I'm not as good as
My head hurts. I can't.
To show the other, show that this is also a subset of a to the m. Take some. Take an arbitrary element of H. I'll call it H dashed. Do I want to call it H dashed? Yeah, I suppose. Okay, now what happens now? What is H dashed? Can I write it as a to the some power? Why?
You just said that A to the m generates.
No, that's what I'm trying to prove.
Yeah.
But you've just said obviously.
Yeah, well, I've obviously said that this inclusion is true, and now I'm trying to prove the other.
H, you're saying that
Yes.
every element.
Wait. Mine's just that very last thing you written. Is that H
Yes.
dash? Because I'm
Yes.
sure yesterday
Right,
you used
yeah.
that.
And then within the, I don't know what those things are called, the brackets, is that A
Angled
to
bracket.
K? Or is that A to?
This is a to the m.
A to M, oh.
Is it too small to read?
No, it's just.
Then you should sit in the front.
Yeah. If I'm smaller,
Is it okay? I'll make it a bit long.
No, I can see them on the image, yeah.
Okay.
I'm really confused.
That's okay. That doesn't mean I'm doing anything wrong.
No, it doesn't. It doesn't at all. It means that
Okay, let's go on. So I want to prove this. So now this H dash is a to the k for some integer k. We don't know what integer, but it is a to the k, and this is because this h dash is in G. Yeah? I picked h dash in H, but H is a subgroup of G, so it's also so h dash is in G, and because G is equal to brackets A, any element of G has to be like this.
Why did you say this?
Why this? Okay, I'll just set it. So shall I repeat it? Okay. H dash is an element of H. What is H? H is a subgroup of G. Well, if H is a subgroup of G and H is in H, it also has to be in G.
Yeah.
It's a subgroup. Now, what is G? G is going to the very top, the group generated by A, which means that every element of G is some power of A. This definition of these brackets. And because H dash is in G, it has to be some power of A. Okay? And now, I don't know what this power is, but I know that it's an integer. I know m is an integer, actually a positive integer, and so I can do the division, k divided by m. So what's it called? Integer division. And this gives me that, so if I divide k by m, what does that? That means that k is m times q plus the remainder. Okay, q is some whole number, and the remainder is also some whole number, and moreover, the remainder is less than m. I was dividing by m. The remainder is something between 0 and m, but less than m. Okay? Number theory. Now, and now, it's really going fast. Picking up speed. Look. So, what is h dash? It's a to the k. What is k? mq plus r. So this is what? A to the m to the q times a to the r. Okay, so what is this? So what is this? Observe. This one is in the subgroup. A to the m is in the subgroup. This whole thing, a to the m to the q, is in the subgroup. Therefore, a to the r is also in the subgroup, because a to the r is what? A to the m to the minus q times h dash. So this is the inverse of something in h. This is in h, so the product also has to be in h. Now, yes. Okay. So I've got this element, which I'm claiming is in h. I take its inverse. That's that. I times it with something in h. The product also has to be. So this is in h. Now, what does that say about r? Can r be m?
I don't understand.
No.
Why did you take the inverse?
Why do I take the inverse?
Yeah.
Well, I take the inverse because I want to know what AR is. A to the R. A to the R, it's like I'm solving this equation, right? I have this on the left, this on the right, and I want to solve it for A to the R. So,
Oh, yeah. Oh,
okay.
can it be M if you don't have it that way?
It can't be because I said no.
Yeah.
Can it be, so what can it be?
Anything less.
No.
0.
Why? Because A to the R is in, so what was M?
The
M was the
smallest
smallest.
Oh,
positive.
M was the smallest positive one.
Yeah.
That was in H. R is smaller than M, so it can't be positive. And if it's not positive, it has to be 0. Okay? So, as M was the least positive integer,
It's fine though.
necessarily R is 0. A to the R is in H. R is smaller than M. Can't be positive. So M was the smallest one. Okay. But now, that's it.
Yes.
So R is 0. So this is the identity. So I'm left with just this. Now I have to go back and recall what I wanted. Now I've made it larger, I can't fit it all. She's not looking anyway, so yeah, so what I wanted is that H dash also belongs to, yeah. What did I want? I wanted to show that when I take anything in H, that was that thing, it will also be in the bracketed AN, which I proved, and that's it. Okay, next.
It's hurting my head though. Is there some sort of
What?
like I don't know because it's also general.
Oh, you want a specific?
My brain can't get around the fact that they're going to be.
Well, this is maths.
Okay, thank you. It's very helpful of you. Yeah.
So this is telling us what all the subgroups of Z are.
Oh, that's a word.
I know. I've been trying since I've been trying for like 3 years. I just can't say it. My mouth doesn't do that shit.
I did it.
Oh, that's actually.
Subgroups of Z are Z.
Sorry.
Oh, here we go. Subgroups of the.
Okay. Z is a cyclic group,
Yeah.
additive, generated by 1. Okay. What are the? All its subgroups have to be cyclic, so they have to be generated by some element. So the one generated by 0 is 0 times Z, so that's all 0 multiples of Z. So that's only 0. Generated by 1 is 1 times Z, so that's all 1 multiples of integers, so that's all the integers. Simple. 2Z is all the even numbers. That's a subgroup. If you add 2 even numbers, you get an even number. Generated by 2, because if you take 2 plus 2 plus 2 plus 2, you're getting all the positive ones. If you take minus 2, minus 2, minus 2, minus 2, you're getting all the negative ones, generated by 2. The one generated by 3 is all the multiples of 3. And there's no other one, because each of the subgroups has to be generated by an element of Z. And if you take a negative one, and you're going to get the same thing as the one selected. The one that's generated by minus 2 is the even integers again. Okay? So it doesn't give you any extra one. Okay? Now, an example of this. Okay, so you get a subgroup of Z, which is well, you're trying to show that. So what is this going to be? So what you're looking for among Z is this M. Yeah. So this M, that translates into the least positive integer that is in the subgroup. Okay. So if you have all even numbers, it's going to be 2. If you have all the multiples of 3, it's going to be 3. So the smallest positive integer that's present there will be the generator. Okay. End of example. Hmm? Or if you have another example, if you have all the rotations of the square.
No, because the problem is the integers, right? A is 1. Yeah. So then, if you increase
He's
the
also
n,
saying,
then it's not going to change anything. You have to change the a. That's what I'm saying.
Yeah, okay.
yes, yes,
So in
we
that
have
case,
different A's.
That's
if
what
you
I
want
think
an
that
example
says.
where A is not 1, think of all the multiples of 6 as a subgroup of all the multiples of 2. So all the even integers is a group. All the multiples of 6 is its cyclic subgroup generated by.
But then, so then the a
And then A is going to be 2 and M is going to be 3 because 2 plus 2 plus 2, 3 times, is the least
I
one.
think that's what's confusing me about thinking
Probably.
of powers in the normal sense. But because we agree yeah, because that's additions, and actually I'm thinking of 1 to the power of 4 being like 1 times 1, which would be 1 plus 1 plus 1, which would be 4. That's right.
Right.
Yeah,
so now there are a couple of oh my goodness. Okay, so now there are a couple of statements about cyclic groups and generators and orders of the elements of these groups, which will be useful later. So just sit back and observe these statements, and you won't obviously understand why we want them, but it'll become clearer later because we'll be using them for more advanced theorems. Okay, so the first one is proposition 12.12, which, if it appears, is so we want to know orders of elements. Okay, well, okay. So now we're looking at finite groups. So we start with a cyclic group of some finite order n. And it's generated by its element A. Then A to the K is 1 if and only if K is a multiple of n. Okay, so again, if I have
You started a proposition in box, and you did say it.
Yeah.
a proposition is a kind of a theorem, except it's called a proposition.
I'm not sure about
Okay.
this box.
That's
I
fine.
think it should,
That's a
I
fine
think it
answer.
should be in a cloud.
Yeah, a theorem is another kind of a theorem, but proposition is like a smaller kind of a theorem.
I'll put a small box.
Like a baby theorem, yeah. Well, like an adolescent theorem. Like a baby theorem is a lemma.
Yes, that's true.
Okay, so Right. So what is this saying? This is saying that you've got. So what is it? So you've got. Well, okay. So what is? I mean, what does it say?
It says what it says.
So what are the elements of G? Okay. The identity a squared, a to the minus n minus 1. Okay, so this is not part of the proof. This is like an illustration. So the proof is only starting later. So if you start with the identity, times it by a, times it by a, times it by a, times it by a, you're still getting, yeah, and then you get to n minus 1, and then times it by a again, you get back the identity, because you already have n. The order is n, so 1, 2, 3, 4, n. Now you can't get anything else. So this is what this theorem is saying. The elements look like that. It's not
Yeah.
So kind of we know that. So well, maybe this is part of the proof. Okay, so a to the n is the identity. And if k is some multiple, so x for some multiple of n, then a to the k is a to the n to the s is e to the s is e. Okay. So that's the if. Now we need to prove the only if. The bag's open. The bag's open.
Why have we got A to the end? Right. Oh, yeah. Because K is effectively N. I see,
Yeah, no, it's kind of part of the proof. Okay, so it's generated by A. So A is there. And once you run out, you go to E, you start again.
Yeah.
This is why it's called cyclic, because it goes like
Yeah.
this.
I got distracted.
So this was, so this proves the if. Pardon? Why I to the n is the identity? Because, okay, G is generated by A. Okay, so G is the identity, and that times A, and that times A, and that times A, and that times A, and I keep going. And now I've exhausted everything because I know I'm only going to get n elements, and I've already had n elements, so the next one has to be this one. So if K is some multiple of n, I get the identity. Now, if I get the identity, then I divide K by n. Get a remainder. So the identity is a to the k is a to the n to the q times a to the r. Now this is the identity. So this is a to the r. But what is r again? R is between 0 and n. So it's one of them. It's got to be 0. No, what am I doing?
Why? We know what you mean.
You people are distracting me from, I mean, r equals 0. Yes. So what's that prove? Yeah, that proves that k is a multiple of n, yes.
Yes, it is.
So k equals n times q. Okay. Okay, so one way, what I'm trying to say is that if k is a multiple of n, and I do a to the k, I get the identity. And the other way I'm proving that if I do a to the k and get the identity, that k must be a multiple of n.
Yeah.
So now I have both ways.
Yeah.
And the next property that we're going to need is a proper theorem. Again, we have a finite cyclic group.
You're not sure where you're sorry, we're distracted.
Yes.
Don't ignore us.
Just say don't ignore us.
No. I started the sentence and then I changed my mind about it.
Now, so okay, so now we know what the order of the generator is. It's n because it generates the whole n elements. But this theorem gives us the order of anything else. So any other element in the group looks like a to the k. Then the order of b is n divided by d, where d is the GCD of n and k. Okay, so this fully gives us all the orders of all the elements, and consequently also all the orders of all the subgroups of the group. Because every subgroup is cyclic, and so its order is equal to the order of the element that generates it. So then you have exercises in the book that tell you, take this group, list all subgroups, and you can do it by something like that. No, it's enough if you understand and you can recreate. Now,
That's assuming a level of maths I don't.
well, that's why you're here, because you want to get there. Now, what is the order of B? The order of B. So it's a theorem about the order of B. What was the definition? We had it yesterday, I think. What's the question?
So,
What is the definition of the order of B?
oh, the element.
The least positive.
The least end such that
B to the M equals E, I think, off the top of my head. Yeah, something like that.
Exactly. Yeah. So I keep timesing B with itself, and the first time I get E, that's called the order. Okay.
yes.
So what is this? So what is this E? E is B to the M. What is B? Well, B is A to the K.
Are we assuming that M Thanks.
I'm not that.
Okay, so maybe I should set aside the case where K is 0. If K is 0, then the GCD of N and 0 is N, and its order is 1, and it all works. Okay, so now we can assume that K is bigger than 1. So, also, so this is this, so, okay. But now we have proposition 4.2. Does anybody remember proposition 4.2? I don't.
We didn't have a proposition. Is it proposition 4.1?
Yeah.
Which, off the top of my head, was A to the K equals E if and only.
Oh yeah, 4.12.
Oh, is that what you meant?
Or
I'm
words to that
looking
effect.
for 4.2 and I don't think it exists. Oh no, it does exist.
For example, 4.2.
Proposition 4.2 also exists.
Does it really well?
Yeah, but we definitely haven't done that. Like it's got cis in it. I don't know. Like,
The opposite.
Okay, so proposition 4.12, it was this. We have some power of A, which is the identity, means that the power is a multiple of n. So the same thing happens here. We have some power of A, which is k times n, nth power, equals the identity. So km has to be a multiple of n. So km is a multiple of n. Okay, so n divides km.
it's like you're starting a table.
And A divides km. So now from number theory, you know that if D is the GCD of n and k, then and n divides km, then n over D divides km over D. Or something like that, you know, from number theory.
I'll accept that.
You've got so much faith in that.
We do not. Oh yeah, because n is on that side and k is on the other. Yeah, that's fine. That's how we do it.
No, it's actually, that's true for any numbers. That's true for any numbers, says Alicia.
I do.
As long as,
Well, it's D is a divisor of the.
yes. Okay. Yes, this is true for any numbers. What is not true for any numbers is that this implies that n over d divides m. But this is only true because the GCD of n over d and k over d is 1. And the GCD of n over d and k over d is 1 because d is the GCD of n and k. Okay, so this goes back to number theory. If you don't remember, I don't have the time, unfortunately, now to reprove. So what have we done now? Oh, now we haven't finished yet. Okay, so we have n over d divides n. Okay, this is actually yeah. So n over d divides n. Now we're looking for the least m, and the least m, positive m, that divides n over d. That is a multiple of n over d is n over d. Okay, so the least m, which is a multiple of n over d, positive m, is n over d itself. Yeah, and then, so yeah, so this could be it. Now, we only have to show that if you do b to the n over d, we actually get the identity. But if I do b to the n over d, I get a to the kn over d, which is a to the n to the k over d. And a to the n is 1, so this is e to the k over d, so this is e. So, yes. Okay, so I'm trying to find the idea of this. I got lost myself. The idea of this, I'm looking for what is the order of m, of b, sorry. So I say m is the order of b, defined as that. Now, if m has this property that b to the m is e, then we derive that m is necessarily a multiple of n over d. If m is necessarily a multiple of n over d, and I'm looking for the smallest m, I can try n over d itself as the first candidate. And it turns out that it works, so everything's fine. So it must be this. Any questions? Almost finished. Corollary is a kind of a theorem.
Is everything a kind of a theorem? Yeah.
No.
I thought a corollary was just something that went alongside something.
Corollary.
It's not
Isn't it? And I'm sure that Killian told us it was like an observation.
Observation is a kind of a theorem.
Yeah.
Yes.
Name something that isn't a kind of a theorem.
An assumption, hypothesis, a proof, a false statement, a definition.
Yeah, you see.
Is a rabbit a theorem?
Pin
A rabbit is not a theorem, no.
Yes.
I know he has. I know. To be fair, I was checking. I wasn't trying to catch him out. I was checking.
No, I think you're trying to catch him up.
No.
It's too small.
That is not.
You said that.
No.
You just said that. Oh, that's offensive.
Who do you recall?
Well, we finished short that the sound was being recorded.
I mean, I hope so.
Oh.
Something missing there. Okay.
The generators.
Not anymore. Sorry, it's in a box. I'm alright.
Zero.
You're going to hate my culture, so I'm just going to box it all the
No, there's another condition.
Well, why are we not having zero though?
Because zero doesn't generate. Okay, so if I take Z12.
Have you read it?
I have read it.
Yeah.
So what are the generators of Z12? Okay, if I take 0, I keep adding to 0. 0, 0, 0, 0, 0, 0. No, not a generator. Okay,
Well,
1.
What even said zero is
1 plus 1, I get 2, I get 3, I get 4, I get 5, I get 6, I get 7, I get 8, I get 9, I get 10, I get 11, I get 0, I get everything. Generator. 2. Is 2 a generator?
No.
2, 4, 6, 8, 10, 0. 2, 4, 6, 10, 8, 0. No, I get only half of them. Not a generator.
3.
Is 3 a generator?
Yes.
No.
3, 6, 9, 0. 3, 6, 9, 0.
Oh,
I'm not getting anything.
I was guessing. Even though I've read the book.
4.
No.
Why not?
480. 480.
Exactly.
Or it's
5. 5. Is 5 a generator?
Yes.
Yes.
Why?
Because
the GTD of 5 and 12 is 1.
So I get 5, I get 10, 15 is 3, 8, 1, 6, 11, 16 is 4, 9, 14 is 2, 7, 0. Is that everything?
Yes.
yes.
So 5 is a generator, gives me everything when I generate. So yeah. So if I have something that is relatively prime to n, I get a generator. Otherwise, I only get some of the n. So 2, 3, 4, not relatively prime to 12. 1, 5, 7. What else? 11. That's it. Those are the generators of Z12. And that follows from that because what is a generator? A generator is a thing whose order is n, and its order is n if and only if d is 1, and only if d is 1.
D is 1.
Yes,
Because if they're not,
that's very illustrative.
It's,
Any questions?